Let's build a k-means clustering model in Python to help you better understand how it works. K-means clustering is an unsupervised learning method, which means you give it data that has no labels, and it learns to find secret patterns within the data to make predictions. And this is one of the most important and helpful machine learning models for finding groups within your dataset, like separating customers by their shopping habits or sorting images into similar sets when you don't actually know the groups ahead of time. So today, let's break down exactly how to make your own step by step. Let's start by diving deep into how k-means actually works. First, as with everything, before you start running your k-means model, you must do a bit of preparation on your data. We want to make sure that all of our features are numeric because k-means clustering works with things like distances and averaging. And then we usually want to standardize the dataset so all the features are on the same scale and one column doesn't dominate just because it's so large. Now, once your data is in this nice standardized numeric form, you need to choose how many groups you're splitting your dataset into. In k-means clustering, we call this number k. At this point, the model itself does not know what a good k looks like for your data, and your job as the coder is to choose this number. And as you're deciding, it's logical to want to test multiple different values of k and compare the results. And this is exactly what data scientists do. One common strategy of analysis is called the elbow method. And this is where you plot all the values of k you are considering versus the amount of error they cause in your model. Obviously, you want to minimize your error as much as possible, but you also don't want to be creating lots and lots of unnecessary groups. So to choose k, find the elbow of the line on the graph. And this is the number of clusters that perfectly balances the error and number of groups in your model. An alternative to this method is called the silhouette score. This method measures how well each point fits into its assigned cluster by measuring two things. First, how similar and close it is to its currently assigned cluster, and how far it is from other clusters. For every single point in the dataset, you compute A, which is the average distance to points in its own cluster, and B, which is the lowest average distance to points in any other cluster. And then the silhouette score follows this formula, which gives us a silhouette score between -1 and 1. We compute the score for every single point and then average it for the whole dataset. A silhouette score around 1 means the clusters are very tight and well separated, and a silhouette score closer to -1 probably means your clusters aren't behaving very well with the data you have, so you probably want to try out a different k value. Now let's get into the k-means procedure itself a bit more. Once you have your dataset, the first thing the model has to do is initialize the centroids. In k-means clustering, we call a centroid the center of any given cluster. So the very first thing the model has to do is initialize the centroids because it cannot assign any point to any cluster until it has some starting guesses for where the centers of those clusters are. In the most basic version of k-means, you just pick k random points from your dataset and declare that these are the initial cluster centers. This seems quick and easy, but because of the randomness in the situation, all the cluster centers may end up crowded in one region of the data or in just generally bad positions. And this can slow things down a ton in your model or just lead to worse final clusters. K-means obviously would still try to fix those initial starting points as the model goes on, but we can do better at the start. And this is exactly what a model called k-means++ tries to do by taking a more careful approach to choosing the initial clusters. In k-means++, you still choose that very first centroid from a random point in your dataset. But after that, every new cluster is chosen using information about how far points are from the cluster centers you already picked. After you have that very first centroid, you look at every point in the dataset and measure how far it is from the closest center and then square those values. Points that are far away from a centroid get large square distances, and points that are closer get smaller distances. Then, instead of picking the next cluster centroid completely randomly, you pick it with a probability proportional to those square distances. So points far away from all the existing centroids are more likely to become new centroids. You repeat this process until you have your k initial centroids that are spread out over the data. Once you have those centroids established, the algorithm enters its main loop, which always consists of two main phases. First is the assignment phase. In this phase, you go through every data point one by one and measure its distance to each centroid, usually using squared Euclidean distance, which just means you square the differences in each feature and add them all up. Then you find which centroid is closest and temporarily assign the data point to the cluster for that centroid. And after this pass, every point in the dataset has a cluster label that basically says, out of all the k centers, this is the one I belong to right now. The next part of the loop is the update phase. And this is where we better adjust the centroids to match the assignments we just made. In this phase, you keep all the labels fixed, but you recompute each centroid by taking the average of all of the points assigned to that cluster. So for cluster J, you collect all the points whose label is J, add them up feature by feature, and divide by the number of points in that cluster. That gives you a new location for centroid J, which is the average of all of its current members. Intuitively, the centroid moves to the middle of its current cluster based on the latest assignments. In both of these phases, k-means is continuously trying to make each cluster as tight and separated from the others as possible. The way it measures this tightness points at any given time is called the within cluster sum of squares. To find this error, you take every point, look at the centroid of its cluster, compute the square distances between them, and add them all up for each cluster. And this is the value that we're always trying to minimize as much as possible. The two phases of the main loop keep going back and forth until a stopping condition is met. And this stopping condition is when the algorithm settles, which usually means one of two things. Either the cluster labels stop changing each time, so each data point is picking the same centroid as last time, or the centroids only move a very, very small amount between one iteration and the next. And in the code, you can also set a hard cap on the number of iterations the model does. And that is the heart of a full k-means clustering model for you. So if you'd like to see this coded out in Python, then stay tuned for part 2.